In this video, we're going to cover our last fluid property, surface tension. Surface tension, we give the Greek symbol sigma, and it has units of force per length. So in SI units, that's newtons per meter, and in English units, it's pounds per foot. And surface tension arises in liquids because the attraction between liquid molecules that we call cohesion. So for example, if we have a free surface like this, which in these diagrams you'll often see an upside down triangle with a couple lines under it to denote the free surface, or say the water surface. And if we look at a molecule that's down here within the volume of the liquid, cohesion is going to act in all different directions because the molecule is going to be pulled in all directions by the fluid around it, or by the liquid around it. So you'll have forces going in all directions like this. And if you integrate the forces around that individual molecule, you'll get the sum of the forces, or the net effect on the molecule is zero. So there's no effect of the cohesion on the molecule within that liquid. However, if we look at a molecule right there at the surface, something different arises where we still have pull to the sides and the pull downwards by the surrounding molecules in the liquid, but there's nothing to balance it at the top. And so at the surface, the cohesion forces from the neighbors that are within the fluid are unbalanced and pull the molecules to the sides and down. And this stretches the cohesion to neighbors along the side and increases the pull. And it tends to act like a spring. So if you want to pull that molecule up, it's going to go back down. It's not in equilibrium. It's going to go back down and come to an equilibrium state. So that pull is very much acts like a spring. And that extra pull is what we call the surface tension that we've given that Greek symbol sigma. Okay? So a quick example of an air bubble in water, and what we're going to do is take a bubble and we're going to slice it along the middle. So we have half of a bubble. It's going to look something like this. Okay? And it's going to have a pressure inside the bubble. We haven't talked about pressure yet, but pressure has units of force per area. And there's going to be another pressure outside the bubble. So we have PO for pressure outside, and PI for the pressure inside the bubble. And if we take that slice, the surface tension, again, their free surface now is along this boundary, along that interface. It's going to act along that boundary. So it looks like a linear force that acts along the edge of our slice, like this. So that's going to be our sigma. So this is now sigma. That's our surface tension. And again, it's force per length, and so we're going to multiply that by the diameter 2 pi r. Okay, so that's our free body diagram for the bubble if we sliced it in half. And so ultimately for statics, we want the summation of the forces equal to 0. So we put that together. We have Pi minus Po. Again, pressure, which we'll go over in the next lecture or the next video, is force per area. So we need to multiply by the area, which is pi r squared, the area of the surface here. And then it's going to be equal to sigma times 2 pi r. And we can clean that up and get the expression Pi minus Po is equal to 2 sigma over r. Okay? And this explains why, say, if you wanted to compare a can of soda, like a Coca-Cola, to a Guinness beer, why the bubbles are different sizes. It's going to be dependent on the pressure at which the bottler used to bottle the soda and the inherent property of the liquid, the surface tension. And so we can ideally, if we know those, if we know what the pressure that the beverage was bottled at and that the surface tension, then we can actually calculate what we expect the size of the bubbles to be. So that's a quick introduction that introduces surface tension. And so now we have some of the primary properties that we're interested in, specifically being density, viscosity, and surface tension as major players in fluid mechanics. There are some other properties that we introduced, but these are the three main ones. And in the next video, we'll introduce the first component of our analyses, which is pressure.